Hello everyone, myself Hassan Aftab from Mechanical Engineering. Today I'm here on my topic that is impact of accumulative roll bonding on strength in production of magnesium alloy. Here's the outline for today's topic, starting from the introduction. Accumulative roll bonding (ARB) is a type of surface plastic deformation procedure that can produce ultra-fine-grained, high-strength multi-layer alloys. In the ARB process, two or more metal sheets are stacked together and then subjected to a series of rolling steps. During each rolling step, the stacked sheets undergo plastic deformation under high pressure. Magnesium is one of the lightest structural metals, with a density about one-quarter that of steel. That characteristic makes magnesium alloy highly attractive for application where weight reduction is crucial in the industries. Despite being lightweight, magnesium alloys possess excellent strength-to-weight ratio. They exhibit impressive mechanical properties, including high specific strength and stiffness. As a result, they offer the potential for weight reduction without sacrificing performance or safety. The high strength of magnesium alloys make them suitable for structural application where load-bearing capacity and durability are essential. Weight reduction, the lightweight nature of magnesium alloys combined with their high strength allows for significant weight reduction in various applications. The strength of magnesium alloys allows for great design flexibility. This flexibility enables innovative and optimized design that meet performance requirements. The objective of cumulative roll bonding aims for grain refinement, microstructural homogeneity, enhanced strength, improved mechanical properties, and process optimization. Moving towards the effect of strength in accumulative roll bonding, grain refinement, ARB involves surface deformation that intrudes a large number of deformation bands and boundaries which promote the formation of smaller and more refined grains. In materials with laminar microstructure, such as certain alloys or composites, ARB aims to preserve the laminar structure while refining the grain size. By reducing the grain size, the material becomes more homogeneous, preventing the formation of weak points and reducing the occurrence of necking. ARB contributes to reducing fragmentation of the material. With grain refinements, the material becomes more homogeneous and the distribution of stress becomes more uniform. Increase in hardness and ultimate strength can be attained by refined grain structure, impedes the motion of dislocation, and promotes grain bonding strengthening, resulting in improved strength. So today the research question is how do cumulative roll bonding affect on strength in production of magnesium alloys? So for the research design, we have an experimental method. A milling machine with a roller of 150 mm diameter was used for the experiment. In order to examine the rolling process for the three-layer composite fabricated through ARB and asymmetric ARB techniques, two distinctive materials were utilized: technically pure aluminum grade 1050A and AZ31 magnesium alloys. A composite material consists of multiple layers of aluminum and magnesium was fabricated and subsequently subjected to the ARB process. Each multi-layered sample underwent 5 Vickers hardness tests to determine the micro-hardness. The experimental investigations are complemented by computational simulation using a computer program based on the finite element method. The analysis of interference diffusion is conducted utilizing a scan electron microscopy with a line scan feature. So first, the multi-layer composites went through the surface preparation, then stacking, then the accumulative roll bonding, and the asymmetric accumulative roll bonding. During accumulative roll bonding, the thinner sheet experienced more surface deformation compared to the thicker sheet. As a result, the thinner sheet undergoes a higher strain and accumulates more significant microstructural changes, such as grain refinement and texture development. Thence, the material go through the cutting and then again to the surface preparation, and these happen in 3 cycles until unless we attain a final product as a desired shape. So after this experiment, we have some finding and limitation. Coming to the finding, AARB successfully achieving bonding between the layers of different thickness. AARB helps to reduce fragmentation in the material. The asymmetrical deformation include plastic flow and strain distribution, minimizing the occurrence of localized fracture and fragmentation. ARB contributes to an increase in both UTS and hardness of the material. The refined grain structure and increased dislocation density lead to higher UTS and hardness values. The redistribution of strain and the presence of a gradient microstructure results in a more favorable stress distribution and resistance to crack initiation and propagation. It results in an overall increase in the material strength. The combination of factors such as grain refinement, bond between layers, and reduced fragmentation contributes to enhanced strength characteristics. ARB achieves grain refinement in the material. The asymmetrical deformation induces strain localization and promotes the refinement of the grain structure. Moving toward the limitation, ARB requires specialized tooling and equipment to ensure precise alignment of the layer during the rolling process. This requirement adds complexity into the process and may require specialized expertise. ARB can be more complex with dealing an intricate or non-uniform geometrical shape. This process is typically easier to implement for flat or sheet-like materials. However, when working on a complex shape or three-dimensional components, the application of ARB becomes more challenging. Meticulous management for maintaining parameters. ARB demands for control of process parameter to achieve desired results consistently. Parameters such as loading reduction, number of cycles, annealing condition, and strain distribution need to be carefully controlled and optimized. Here are some references. Thank you so much.